I'm going to record this meeting now. You can see, everybody can see my screen?
Yeah, this is Wayne. I can see it, or at least I see all the files, little
That's
pictures,
good.
thumbnails. You're not recording now, are you?
Yes, I am.
Okay, I'll be
Okay,
quiet.
so here is the basic, um, we're in MATLAB, we're running EEG Lab, we're in the Beamer GUI, and then we hit run. And now you see the BrainMaster GUI, and this video is going to walk you all the way through almost to the end. So what we do is um, I'm reading a file, and this is from Harry Karasides' data. And then there's a click through, and the file is read. And now I can hit the data set, and you see the data sets. And then I hit View EEG, and I want to add the information about the channel location. So I go into my local directory, which has the channel. There it is, Avatar 1020 Cap. I open that, I hit OK, and then I can view the EEG, and there we see the EEG loaded in, and it's got the marks in it. Those would be from Capito. In this case, they're from Excellent Brain, but it doesn't matter. And what I'm starting to do now is I rejected a piece of noisy data and then saved it again. And what I decided to do now is to actually start rejecting more noisy data, because you've got to get rid of the real nasty noise in order for the ICA to work. So see how it made that boundary where it chopped that piece out? So now you go through the data, and I'm going to remove a few eye blinks, although you don't have to remove eye blinks. You shouldn't really bother because the ICA will take the eye blinks out. But where you see other noisy, like really nasty junk like this, sweep it out. This is what I'm doing with the left mouse. So you do want to walk through the EEG like this and sweep out any obvious garbage or noise like I'm doing here. So I move forward. You can sweep to the left, you can sweep to the right, and you can redo a marker. If you click on a marker, it'll redo it. And so now I'm walking through, and it takes a little while. Here's another one. The more of these really nasty things that you get rid of, the better off everything will be, because otherwise the ICA will try to categorize them and treat them as if they are components. And a little later on, as we look at the components, we're going to see that you throw away components whenever you waste them on noise, artifactual noise. And so here again, I'm sweeping out this area. Now I'm going back because I erased the mark when I clicked on it. So you got to be careful of that. You can leave some of the junk in there, but the best practice would be to really go in there and pull out any of this kind of garbage. So that's going to take a certain amount of time. And again, these things that just jump out, you can leave quite a lot in there, of various things. You don't want to, one of the themes here is you don't want to throw out the baby with the bathwater. You don't want to throw out too much. And so this, again, just for this demonstration, I wanted to make sure I got as much of this as is reasonable out of there so that the ICA can work. So I hit reject. Now you see there's 103,000 frames. It used to be 120 something thousand frames. So 20% of the frames just kind of got knocked out. And now you look through it and you see these boundaries that separate where you chopped out the event. So this artifacting literally chops the chunks out of the EEG. And now I'm extracting the events. I just extracted events 1. I imported events 1, and now you see the aux1 channel has been removed and replaced with event markers. Now I hit events 2. I import events 2. And now you see that the 2s are marked in addition to the 1s, and channels, the last 2 channels have been removed. So we've converted the marks from Capito or Excellent Brain and converted them into marks for events. Now we run the ICA, and this is going to take a little while. So this is a learning algorithm that attempts to identify dipoles in the EEG, and it uses a learning type of iteration so that it finds the most prominent, obvious sources and then looks for them in every channel, but it looks for them in such a way that if there were a dipole in the brain that produced this component, that's how it would be picked up on the different channels. So it actually uses kind of a forward solution concept to look for how that dipole expresses in different channels. And so it can be positive in some channels and negative in other channels. But basically, the shape of it, the appearance of it, is assumed that it's appearing at the same kind of wave period and time, and overall shape in all the channels, but just being reflected using the volume conduction as by what we call a transfer function. So it's trying to learn, and right now the learning rate is 18 parts per million, and the learning rate wants to go down to 1 part per million. And you can of course adjust this, but this gives it a good reliability, and it's worth waiting the extra time to get the best estimate that you can. Now, because of the way the mathematics works, you actually only get as many components as you have channels. So in this case, we're going to wind up with 20 components. That's not the same as 20 channels. Each component exists in all the channels, but it reflects differently in each channel, and you'll be able to see component maps and all that kind of good stuff very shortly. So this is one of the biggest steps in time, is this ICA, and we do this because it can effectively remove eye activity. The major components we want to remove with the ICA are eye, and alternatively things that are clearly noise bursts, and we'll see some like that very shortly. Okay, the ICA's done. We're going to view the components. So now we're going to get 20 scalp maps. Each component is scalp mapped, and you're going to look at them one at a time and decide whether you want to throw them out or not. Now, number one, when we look at it, it has this characteristic appearance of red dots followed by blue kind of canoes. Those are eye blinks. Every one of those is an eye blink, and those are the trials, the 160 trials. So we're going to reject this. So we hit the reject button and close this window. We're going to get that pulled out of the data. Those are the main eye blinks. Number two, we look at, and we see that it's got this weird frequency spectrum we don't completely understand. And we also see it's almost all in this one trial and not much else. So I'm inclined to remove it. You look at 3 and you see it's got a 10 or 11 hertz peak, and it's all over the data, all through the trials. This is a rhythm. This is without a doubt an alpha rhythm, so we keep it. This one also, you see it in this one trial, but not much else elsewhere, so we are going to get rid of it. It's kind of getting lost in the noise. This one, you see, it is also everywhere else. It's kind of the bathwater. So I'm going to hang on to it because I don't want to throw out the bathwater with that particular baby. Here's another one. There's a lot of what I call bathwater. There's a lot of good data showing that it's some sort of thing. It might be eye related. An argument could be made to get rid of it, so I'm going to get rid of it in that case. That's just your basic eye movement noise. Here's another one. Has a peak around 27, 28, so it's probably beta activity. And looking at how it distributes in time and space, it looks like a rhythm. So we're going to keep that one. And we basically go through all the components. Towards you get to the end, they're pretty much real. Again, there might be a little baby in the bathwater, but we don't want to throw the bathwater out. just to get rid of that one. So we do know we have one trial that's a little noisy lying in there. Probably should have chopped it out. But other than that, these components are probably good, good finds. This one especially, this central rhythm, it is at 11, 12 hertz. It's an SMR or an alpha rhythm. We're going to keep it. Because a lot of ERPs is the locking of rhythms. There's studies showing that the ERP is not that you made the brain act that way. It's that you synchronized the rhythms, the alpha waves, the beta waves. So these components could contain the ERPs in terms of the phases of all the rhythms, and the phase is preserved. So we're going to remove 1, 2, 4, and 6. We hit accept, it removes it. It renames the file pruned with ICA. And now we see we have another data set called file pruned with ICA. And when we look at it, we see that it's been cleaned up. There's no eye blinks in there. You can go page after page after page, and the eye blinks are all gone. Other than that, there's a lot of information in there, a lot of different, these are across the channels with the components, all the components removed. And there was that bad trial we saw with that big thing. So we're going to filter it, and you press filter, and it's filtered, and then you can view it. And when we look at the filtered, we'll see it's filtered at 20 hertz, which is what Tado recommended. And here we type in filt. So now I have a file that's filtered, and I'm going to look at it. And as you'll see now, the file itself it's smoother now because it's been filtered down at 20 hertz. And you go page after page, and again, you've got all this information, all different frequencies, but the eye blinks are pulled out, and it's filtered down at 20 to smooth everything out. And so now we can do create ERPs 1. And we push it, and it renames the file with the word epoch. We hit OK, and we're going to have a baseline of -100. And we let it go, and we go through and we hit overwrite. The second time you see the file name, hit overwrite, so it doesn't make more than you need. And now you see the epochs, and when we view it, we knew we need to use plot channel data scroll. The GUI kind of didn't work on this particular one it used to. So now you see epochs broken up. Wherever there was a 1, you have a 100 millisecond pre-stim, and then you have the data epoch after epoch after epoch. This is how MATLAB creates the epochs. Now we're going to go back to the original filtered and we're going to look at it. And there you now see we have epochs 2. So we imported the events 2. Looks like I did it twice. That's why that one looks confused. Now we're going to make sure we rename the file, and we have epochs 2. And overwrite the file second time you see the name. Otherwise, it'll actually create 2 data sets with the same name. And now you see, again, we got to use plot, channel data scroll. And now you see the epochs 2. So these are just the epochs built around event number 2. And in this one, it's common and uncommon stimuli. So that now gets us to where we've created the ERPs. And that's the end of this particular video. And then the next video will show you how to view and analyze ERPs. So I'm going to put minutes, and then we'll have that material. So this is the second piece. In this one, we have created the ERPs, and now we want to view them in different ways. And there's ERP map series is one way to do it. And so first of all, look at which data set you're on. Right now it says ICA Filt epochs. That means that's the event 1. And I want the ERP map series for event 1. And now you put in your latency. So I put in 100, 200, 300, 400 and hit OK. And now I have scalp maps of the responses to event 1 averaged as averaged evoked potential maps of the time series. So these aren't alpha, beta, etc. These are the actual ERPs as time series. Now I'm going to number 2, the event 2 epochs, and now I'm making ERPs. So these are the ERPs to the uncommon stimuli. And on the left, I think I got it right, are the ERPs to the common stimuli. So you see there's a big difference between common and uncommon. And what we're interested in is what is the difference at 300 milliseconds. And as you can see at 300 milliseconds on the right, it's a little less blue than on the left, which means right minus left is going to give us a P300, okay? And you need the difference to get a P300. So we hit create difference ERP, and then we say I want to average data set 7, and I want to average and subtract data set 6. So I'm going to take the uncommon and I'm going to subtract the common, and this one now gives me a scalp array of ERPs, event-related potentials. So if you double-click on one, or single-click actually, now you get a magnified event-related potential, and in the purple you see it's event 2 minus event 1, and at 300 milliseconds approximately, you see this peak. There's your P300. So what we can do is with this tool, you can go Tools, Data Cursor. So we pull the data cursor, and then we click down on that peak, and we see that it is at 281 milliseconds, and it's 2.419 microvolts. That is your P300. So someone who can compare that in this paradigm would be able to detect that is basically a good P300. It's a good latency. I think the amplitude is reasonable. Now we have other options. You can do component maps, and you can do them in 2 dimensions. So here we're going to see, and we're going to ask for the 16 components that we salvaged. These are surface maps of the component of the response to event 2. See on the bottom it says epochs 2. So here's component 1. It's a posterior peak of the magnitude of that component across the head is greatest at P3. And so those are the maps of each of the components. You got 16 evoked potential components, and they can be viewed then for event 1 or event 2. And then we have you can look at component spectra and maps, and there you give the epoch time range, and now you get the spectra of each component, and so you can see which frequencies they contain specifically. And that largest component is at 10 hertz. There you see the peak at CZ, and also a peak at T6, basically. Then we have component activations is a time series of each component. So it looks like channels, but they're not channels, they're components. And as you go across, you can see then the relative shape and size of the different components. And then there's a lot of different things. See, we're automatically connected right in with EEG Lab. So everything EEG Lab does, we already have. Now here's an ERP image, and this will be component 1. So we blow it up. Now you get per trial. I call it a trialogram. You see across from bottom to top are the different trials, and the pictures presented on top are different than the pictures presented on the bottom. Carlos will recognize this kind of thing. They were going from happy faces to sad faces. So the average ERP, even in this component, does mix up the different types because in addition to being all the same stimulus, some were happy faces and some were sad faces. We can then look at component 2 if we want. And There it's very interesting. You see the behavior across the sessions. And again, it's got some variability from the first. So I just did the first 4 components in this example just to show um, the difference in how they look. And some of the components are obviously more telling than others. And each one reflects a dipole, which means it's a brain region. So component 3, again, very interesting. It has this very consistent negativity at 80 milliseconds. So, it's very likely that this does include, early components as well as late. And then we'll look at component 4. Again, very interesting. It almost is a backwards of component 1 in some ways, in time and in space. It's interesting where 1 is blue, 4 is red, and vice versa. So that's an example of being able to, and if you click on those, they all magnify and all that. So that's different ways, and that's not all the ways. There's many ways to view ERPs, but this shows how to get into it and start.